All right, here's part 2 of the ratio test. So I actually found my notes from last year, which is where I got my problems from, so I included it this time. Sorry, this is the template for the notes. So the examples from the last video came from here in terms of looking at the ratio test with ends. So in the last notes, we did this example, and then I also did what happens with, how do we deal with factorials. So there's all of the information with the factorials. Now, the second part of ratio test is, what do we do when we have a series that has not only n's, but also x's? So on that quick check, you saw there was an n and an x, and people were like, what? That's because I didn't intend to put an x yet. I meant that to be an n. But it is possible to have x's and n's. So what do we do with that? So I wrote here, the two previous examples do not have x's in them. Therefore, when we say they converge, we mean that they converge for all real numbers. In other words, if I know the function that the series represents, the two will look identical forever if I graph them. So for all of these and everything we've done so far that only have n's in them, we were determining whether this series converges or not. The end. Good night. But now that we are going to have series with x's and n's, we're going to be determining for what values of x this series converges. We're going to be asked to find the interval of convergence. So basically now we're going to get a series. We're not going to really be able to apply all of those tests to it because I have an x here, which is going to change the test. If that x is 1, the series might behave in a certain way, but if the x is 5, the series would behave in another way altogether. Let me see if I can make that make a little bit more sense. So this is not the notes yet. This is just a random thing. So for example, if I have the series x to the n over over n squared, if this series, if x equaled 1, then I'd have the series 1 over n squared. Whoops. Sorry, my phone is beeping. If x was 1, then the series would be 1 over x squared, and we would have a converging series. But if x is 2, then I have the series 2 to the n over n squared, and that's going to diverge because the top is growing bigger than the bottom. So it depends on what x is, whether the series will converge or not. So that's the problem we're going to be faced with now, is for what values of x does a given series converge? So we could end up with having to say, oh, this series diverges for all values of x. It'll never converge. That is possible. But most times what's going to happen is our series will converge for certain values of x. We just have to figure out what those values of x are. Okay, so I wrote down here something else to note. We don't even worry about the nth term test. So we're not even using the nth term test anymore because it doesn't apply because of this x. This x screws things up and gives us too many options for what this series is. So when our series has both x's and n's in it, you are going to be asked to find the interval of convergence. In other words, what values for x will make that series converge? The only two tests that you can use for this are ratio and geometric. That's it. Those are the only tests available to you to use. Nothing else is going to work. So in some ways, it's a relief because if the problem says, what is the interval of convergence, you don't have to figure anything out. You have to figure stuff out, but you can jump right to the ratio test and or the geometric series test to do that. Okay, so really first, I guess I should start with the second one because I don't actually need the ratio test for the second one. The second one says find the radius of convergence for this. This is a geometric series. We don't know what x is. We're going to figure out what values for x will make this converge. So let me actually start with that. And then when I do it a second time, I'll do it with ratio test. Notice these other series that I have as examples are not geometric. Geometric series have the form something to the power of n. Anything else makes them not geometric. See how this one x to the n, 10 to the n, that's great, but this n here screws it up, not geometric. This series here has this to the n, perfect geometric, but then that n, not geometric. But this one only has some term raised to the n, so this is geometric. If you're not sure and you need to like double check that, get your first few terms. The first few terms are going to be x plus 5 to the 0, plus x plus 5 to the first, plus x plus 5 to the second, and so on. So my multiplier is x plus 5. So this is a geometric series. My multiplier is x plus 5. Okay, so how do we find the interval of convergence? Well, because this is geometric, I know that a geometric series converges when my multiplier is between 1 and -1. So I'm just going to take that r and I'm going to force it to be between 1 and -1. Get rid of this. So I'm going to say, okay, I know my multiplier is x plus 5. That has to be between 1 and -1 for my series to converge. So therefore, x must be between, subtract 5 from both sides, -6 and -4 for the series to converge. That's it. This one is as simple as that. This series is really geometric. I don't need ratio test. I'm going to show you how to use ratio test instead, just so you can have two options. But this I could have done before. I could have done this, days ago when we had talked about geometric series. If it said, what is the interval of convergence? Find the multiplier, set that multiplier up to be between 1 and -1, and solve for x. In fact, we already did problems like this, I think. So now let's just show that I could do the same problem using the ratio test instead. So let's keep with the same one, and let's just use ratio test to see how it would work before we get to the more complicated problems. So the ratio test says, look at the limit as n approaches infinity of this series, replacing n with n plus 1, and divide by this series without replacing n with n plus 1. And evaluate that limit. Now, when I didn't have x's, what I was doing was I was finding that limit, and whatever number that limit equaled, I would compare that to 1. And as long as that limit was between 1 and -1, my series converged. And if that limit was bigger than 1 or less than -1, my series diverged. Well, this time I'm not going to get a number. This time I'm going to get x's. So let's see what happens. I'm going to reduce this just like I did before. I have the same base with exponents, so this is going to become x plus 5 to the first. I'm doing n plus 1 minus n. Well, what is this limit? I don't have any n's here. So the limit as n approaches infinity, I have nothing to plug in. I have no n. So this limit is just going to equal x plus 5. Just like on the previous stuff, if I had the limit as n approaches infinity of 1/2, I got 1/2. If there are no n's, then the result is just x plus 5, or whatever I'm taking the limit of. So what does the ratio test say? Again, the ratio test says whatever my result is from my limit, that result, the absolute value of it has to be less than 1, which we know means that it itself has to be between 1 and -1. So subtract 5 from each side, or whatever, all three spots, and we get that. Same thing as I got before. So what is the interval of convergence? This series converges when x is between -6 and -4. Just like we got the same answer when we did it with geometric series test. Okay, seems easy. Is it always easy? Oh, not all the time. So let's try this one. This is not geometric, so we're going to have to use ratio test. Again, the good part is we only have one option, geometric or ratio test. This is going to be ratio. So let's look at the limit as n approaches infinity. And because I have a fraction, I'm going to plug in n plus 1. And instead of dividing by this series with n's, I'm going to multiply by its reciprocal. So first I'm going to substitute n plus 1. and I'm going to multiply by the reciprocal. My next step, I'm going to do just like I did before. I'm going to group things up. So I'm looking at similar things over similar things. So my n plus 1, I'm going to be comparing that with n. My x to the n plus 1 over x to the n. So I compare those similar things. These are all multiplied. And 10 to the n over 10 to the n plus 1. I'm just regrouping. So I'm putting this over this, this over this, this over this. All right, now I'm going to figure out what do each of these become. Well, n plus 1 over n, as n goes to infinity, I'm comparing the degrees. The degree of the top is 1. The degree of the bottom is 1. Oops. So the ratio of the coefficients is 1. So this part of the limit is going to 1. This part of the limit is going to become x to the first. Subtract those exponents because I have the same base. This part of the limit is going to become 1/10. Subtract those powers, I get 1/10. So the limit is 1/10 x. Okay, the ratio test says this absolute value has to be less than 1. So what that means for me is 1/10 x. I'm going to stick that between 1 and -1 and find out what x equals. So multiply everything by 10, and therefore x is going to be between 10 and -10. This is the interval of convergence. That means that for this series that I'm given, this series will converge. Whoops, I didn't mean to do that. I meant to do a box. This series will converge only when x is between -10 and 10. If x is 20, this is going to be too big. It won't converge. If x is 30, 40, if x is 11, if x is 10.1, if x is -10.1. So if x is anything outside of this interval of convergence, this is going to diverge. But as long as x is between these numbers, that will be a converging series. That's what ratio test does for us. Okay, let's try another one. Maybe you even want to try to start it and see if you get anywhere. So again, find the radius of convergence for this series. So we're going to look at the limit as n approaches infinity of 3x minus 2 to the n plus 1 over n plus 1. And instead of dividing by the big fraction, I'm going to multiply by the reciprocal. Let's clean this up. Let's put like things over like things. So 3x minus 2 to the n plus 1, I'm going to compare with 3x minus 2 to the n, and n compared to n plus 1. This is going to become 3x minus 2. Oops. Sorry, guys. That is supposed to be n. So this is 3x minus 2 to the first. This is going to go to 1. So my limit is going to be 3x minus 2. To find the interval of convergence, that expression has to be between 1 and -1 for the series to converge. So I'm going to solve this, add 2 to both sides, or all three sides. Divide everything by 3. Oh, gosh. That is the interval of convergence. So, oh, sorry, this said find the radius of convergence. I'll get to that in a second. So the interval of convergence for this, even if the question says find the radius, not the interval, I'm still doing all the same work. So the interval of convergence for this is x has to be between 1/3 and what do we say? And 1. That is the interval of convergence. If they're asking for the radius, they just want to know, like, x is if x is halfway in the middle of this, what's the radius? What's half of the, what do I call it? Like, how big is this interval and what's half of it? Does that make any sense? That's one of the times I wish we were together. Yeah, sorry. I'm looking to see if I have a better way to explain it out loud, but I don't. So from 1/3 to 1, think about a number line. If this converges when x is between 1/3 and 1, that's the interval of convergence. What's the radius? So what's half of it? Well, from 1/3 to 1, that's a total distance of 2/3 the whole way. So the radius is just 1/3 because that's half of it. So the radius of convergence is 1/3. The interval goes from 1/3 to 1. Hopefully that makes sense. It's not the biggest deal. Understanding the interval of convergence is the much bigger deal. Okay, and let's do one with factorials before we stop. What's the radius of convergence for this? So this one is nasty. This one also is a little bit weird, so buckle up. Okay, start with ratio test. The limit as n approaches infinity of x to the 2, replace n with n plus 1, replace the n on the bottom with n plus 1, multiply by the reciprocal of the original. Okay, so let's group some things up. We have x to the, I'm going to reduce this and make this 2n plus 3 over x to the 2n plus 1 times n factorial over n plus 1 factorial. Hopefully you followed in the last notes what we're supposed to do with that. So let's see. If you weren't sure, I'll make it a little bit more clear because I got cut off a little bit. So how do I reduce the factorials? Think about the factorials in this way. N plus 1 factorial means I have n plus 1, and then I'm going to multiply by the term that comes before that, and then the term that comes before that, and the term that comes before that, and so on. N is going to be take n and multiply by the term that comes before that, and before that, and before that. All of these are going to cancel with all of these, leaving us with just 1 over n plus 1. So I'm going to continue this limit. I'm going to have the limit as n approaches infinity. This is going to become 1 over n plus 1. And this is going to become x to the second. Subtract those exponents. 2n plus 3 minus 2n plus 1 gives me x squared. Okay, so what the heck do I do with this? This one's a little bit crazy. This is not one I would expect you to be able to do on your own at all. If you've gotten down to this point, you're good. Think about this for a second. So there is an n left in my limit, right? I'm taking the limit of this stuff, and so far I have not had an n left over, but I do now. So what's happening as n goes to infinity, this whole thing is becoming 0. Is that okay? Well, the ratio test says that as long as that limit is less than 1, or its absolute value is less than 1, then the series will converge. Well, because I'm looking at the limit as n approaches infinity, this limit's going to equal 0 all the time. Well, 0 is less than 1. That means this series is going to converge for all values. The interval of convergence is going to be negative infinity to infinity. There is no x to put between 1 and negative 1. There is nothing to put between 1 and negative 1 because this limit will be 0 always. Because there's still an n left in the thing I'm taking the limit of, and that n is in the denominator, this bottom will get huge, the fraction will get tiny, this basically goes to 0, so it doesn't matter what x is. X could be 1,000,000, and this will still equal 0. So we don't care what x is. This will converge all the time. The interval of convergence is this. The radius is also infinity, because that would be half of infinity. Okay, I hope it makes some sense. We have some practice, so we'll see how it goes.